Welcome to the CCT Output Override Monitoring video. Locations for CCT for literature are found under the Product Literature internal site on the portal, as well as on the Quicklets site. Both of these areas will have help in the PDF file format, which is also the same content as found in online help. The objectives of this video include: what is the Output Override Monitoring feature? We'll explain the CCT components of this feature, as well as what applications use variations of this feature. For the first objective, what is this Output Override Monitor? Let's take a look at a little history. Prior to Release 5.0, PRAC will tune loops even when the output point is in the Opera override state, or any other priority other than 16. This has caused PRAC to tune to unrealistic values. When the override was released, the PID block would exhibit poor control until it finally goes into the retuning state. At Release 5.0, a feedback mechanism is in place to disable the control layer of the PID logic when the output is overridden. When the override is released, the PID would use as a starting point the value that was in the override command. So let's take a look at this as an example in this graph. Let's say this is a cooling output valve. It's currently controlling at 50% open. If someone overrides this valve to 75%, the PID logic goes into a hold state, and it is not doing any PID calculations. Once the override is released, the PID logic goes back into control state, and the PID then starts controlling from the value of 75%. That's the value of what it was when it was in the override condition. So from there, it will tune itself until it finds a satisfactory result. So that's how this monitoring feature works. So let's take a look at it in CCT. I have CCT open with a standard fan coil application. Let's take a look at the components of this feature. First off, let's take a look at our output points. We have a cooling output and a heating output. Both of these have an output control module that utilizes the PID block for its control. Therefore, at Release 5, there are going to be two miscellaneous input points that are actually monitoring those output points. So let's take a look at this cooling output % miscellaneous point. If I look at its connections, we'll see that the output position, output 1, we'll see that it's going to the proportional cooling block as the actual position. So if someone overrides the cooling output point, this cooling % will know what that position is. Another output identifies what the priority is. So if someone does an operator override, the priority now would be 8. When they release the priority, it'll go back to priority 16, the default priority. This priority actually goes to a new block called Cooling Override Check. So if I hover my mouse on top, you can see the tooltip, Cooling Override Check. That is one of the state generator modules. So here's the Cooling Override Check. That's coming from this cooling %. Since I do also have a heating PID, there is a heating output, heating % that goes to the Heating Override Check. These state generator modules are going to monitor these miscellaneous input points. Let's just take a look at these miscellaneous points one more time. If you notice that they have a % in the point name, whereas the actual output points, in this case, have a -O for its output. The actual output point here is in reality the same point as this one. It's the output point that's connected to the output device that it's wired to, but these miscellaneous points do not have a signal. All they're doing is mirroring what's in the output point. These miscellaneous points will provide a priority level, not a signal level. In fact, if I hover my mouse over cooling percent, you can see that the signal is not applicable. That's what the NA means. So there is no signal here. When I go to the cooling output, you can see that there's a signal of 24 volts AC incremental. So they're really the same point. The output point is actually connected to the device, but the miscellaneous point is monitoring the priority level of that output. So we know that these miscellaneous points go to the state generator modules. So let's take a look at the cooling override check state generator. We'll look at its connection menu first, and we'll see that an input is coming from the cooling percent, and what we're bringing in is the priority level. So now this state generator knows that it's not priority 16 anymore, it's something else, which will then identify that this cooling output point is not in its normal priority, but it's something else. So it's not priority 16. It might be an operator override, which is priority 8. Another input which doesn't have a connection is the setup input. And the default value for this one is an OR function. Now I only have one input coming in here from this cooling percent, and usually that's what you're going to have when you have a proportional output. So the OR is what's going to be chosen. So if any of the inputs, but there is only one, if there were more and you had an OR, that would mean any of these inputs would cause the output to go into an overridden mode. So the output of this cooling override check state generator is going to go to the state selection table. So this output is actually a true or false. So if my priority is 16, I am not in an override state, therefore the output is false. If I do perform an operator override at priority 8 or something other than 16, then this is going to go true. So the state table knows about this, as well as the proportional cooling logic. This cooling override check sends a signal to the state table as well as the output control module. Now, if you notice, we talked about the miscellaneous inputs. If you notice on the right side, there's also a section here for miscellaneous outputs. The miscellaneous outputs are not used with this feature, but they may be present for other purposes in other CCT applications. For example, the VAV application uses the stroke time as a miscellaneous output point. And the miscellaneous inputs, that's what's used for this override monitoring feature. And if you notice again, this percent symbol is used for proportional output points. Later I'll show an example that has staged outputs, and they have a different symbol there. They actually use the letters EC, which is the abbreviation for effective command. So when you see a percentage on your miscellaneous inputs, that's a reflection that your outputs are actually proportional output signals. Now let's look at the state table and see how this cooling override check state generator block has an impact on that. So I'll view the state table, and I'm going to look for cooling override check. So there's the state generator module. It's connected to the output overridden port of these outputs. And if it's false, we can see that it has no impact on those output control modules. If the cooling override state generator sees a true signal, then we do have an impact. You can see right here the proportional cooling control module will go into a hold state. The other modules are not affected by this true signal. So for cooling override check, it's the cooling module. If I just look up once, I can see here on the above state generator is the heating override check. If that goes true, then the proportional heating control module goes into a hold state. So that's how the state table is laid out. Now let's look at the proportional control block. First, we're going to view its connections. And we can see right here the two inputs that are coming in. The first one here is coming from the cooling override check, because that's going to be true or false, telling us that the output is in the overridden state. The other input is the value of the override. What's the percentage of the override command? And that's going into an input connection called output position. So we have two inputs into the proportional cooling control module. Now let's look at the logic layer. I mentioned that this module will go into the hold state when the cooling output point is in overridden. So if we take a look at this, I'll make a little bit more room here. If I go into the hold state, so I'll double click on hold, you can see there's a mux block that sends its output to the percent command. So when an override is active on this cooling output, this control module goes into an hold state. Well, let's take a look at the two input connectors. Here are the two that we identified a few minutes ago. Output overridden being true or false, and the output position being the value of the override. So if we unhide these labels, we'll see that the true or false goes into this mux block. Well, let's get a little closer in on here. I'll zoom in this area. So the mux input, the mode input, is being driven by the connector called output overridden. It's either true or false. So let's look at how the mux block will behave. If I double click on it, here's the information. If the mode connector goes true, I'll take input 2. So if the cooling out is ever overridden, this signal goes true, and input 2 then, whatever is on that connection, will be passed through when it's overridden. Well, that looks like it's connector number 7, and that is actually this one over here, which is the actual output position. So if I override this valve to 10%, that 10% comes in, passes through the mux block, and becomes the output point. Well, if I'm not in overridden state, then input 1 is connected. Well, let's find out what label 4 is. So now it looks like if the override is active and it's true, then the value of the override position is sent. If I'm not in override state, then the output of whatever is controlling this percent command right now is passed through input 1, and then it comes back out again. So it's kind of a loop of the current value. So this mux block passes what's currently there, or if it's an override, it'll put that value as the output. Now we also know that when it's in override state, the hold layer is active, but let's take a look at the control layer where the PID block is found. When I go into the hold state and the value of the override is used as the output connector to the actual valve, we can see now, and I'll zoom in a little bit more here on this PID block, we can see an attribute here, an input connector called startup value. And it's got a label of 4. So let me unhide that. So right here, this is the startup value. So when the override is released, whatever value is found here, that's what the PID and the prac feature will use for the startup value. Well, if you notice where it's coming from, it's actually coming from the %command connector. The value of that %command is the value of the override. So if I override this valve to 10%, a 10 is found at this %command, and that 10 becomes the starting value then of the PID block. Now let's see this in action here. So we're going to go into commissioning mode. I'll go back to the application code. And I'm now going to go into commissioning mode, and we'll see this in live action. Okay, I am now in commissioning mode, and if we examine our inputs, set point of 70 degrees Fahrenheit, 73 is zone temperature. I'm above my cooling set point, therefore I'm in cooling control mode. My proportional cooling control module says in control, and sure enough my cooling valve is at 68%. So this is normally how things are running. Well, what happens now if the cooling valve goes into override? So I have Metasys open as well. I'm going to log into the FEC here under the field bus. Here's my cooling out valve. And in fact, I think what I'm going to do is just lower this and we can... All right, normally someone in the user interface is going to do an override to the cooling valve for doing some testing or calibration, whatever they kind of service work that they're doing. So I'm going to do an override, and I'm going to close that valve off completely. So I'll put in 0% for operator override and send that out. Now watch what happens here. There we can see now that the cooling override check went true. The proportional cooling control logic went to the hold state because of the state table. And my cooling output is what I put in override at 0%. This caused the miscellaneous input then to monitor the priority of the cooling output point, which is now at priority 8, to actually set up the state generator to force the cooling module to go into the hold state. So it really all started from this point here going into override. Then the miscellaneous point saw that priority level, which then enabled the state generator to go to true, which told the state table to put the proportional cooling logic in the hold state. So let's just take a look again at this cooling output. I'm going to view its focus tab, and then I'm going to look at its priority table here. And you can see that 8 is the operator override. And if I go to CCT, and if I right-click, let's see if I can see it here in details. View details of the miscellaneous input point. Here you can see the current value for priority is indeed 8. So that's the priority of the override, which then indicated to the state generator that it now is going to go into a true state because I'm using the OR setup here, and it was really input 1 that now is not equal to 16. It's got an 8 there, which then gives me a true out. And that true out went into the state table to put this proportional cooling control logic into the hold state. So if I view the logic there, and I can go and look at the hold mode and kind of zoom into my MUX block, Here we can see a true is the mode, and 0% was what I commanded it to. And the label number 4 right here is the one that came from the output point. So 0 is coming out of my hold logic layer. So if I go into the control logic layer, move this out here now, I go to the PID block, the percent out of this PID should be whatever the last value was. If you think about it, I am not in the control state right now, I'm in the hold state. Therefore, this layer is not active, but it does know that 0.0, which is coming from that hold active layer, is the new startup value. So when I do go back into control state, when the override is released, I'll start from the 0%, and then from there, prac can take over. So let's see how I could show this. I'll go back to the application layer, or the application tab, and we can see that the proportional cooling control is on hold, currently at 0%. So if I go back to Metasys now, and I release this override, we'll see the cooling output. Let's see, before I send that out, keep an eye on this one here. This is currently 0%. When I release the override, it's going to start at that 0 and then start modulating up. Now, CCT has a 20-second display refresh on the computer, the screen that we're looking at, so it may not be real linear, but we'll see what happens here. So I'm going to hit the send button, and the state generator table should go false. Proportional cooling control is in control now, and it looks like we jumped to 56%. So it was a pretty good sized jump there right away. But theoretically, it started at 0 and then started ramping up. We just didn't quite see it very quickly. Now that we've seen how it works with this cooling application, let's look at one more CCT application that uses a staged output. So let me stop commissioning and load up a different application. I'm going to open up this rooftop unit here, which has a 2-staged cooling and 2-stage heating with a proportional mixed air damper. Let's take a look at this rooftop application. The outputs are cooling 1 and 2. These are stages, and for heating there are 2 stages. For the mixed air damper, it's a proportional output. There's only 1 damper output, but there's 2 cooling and 2 heating. If I look at my miscellaneous inputs, I can see that I have 2 for the cooling output points. Notice they use EC, which stands for effective command, for its point name. These are the miscellaneous inputs that are going to be monitoring the priority levels of those output points. And for the single proportional mixed air damper, you can see it has the percent in its name. So the miscellaneous inputs are either going to have percent for the individual points, EC if they're staged. Now, not only is it different there, but let's take a look at the state generator modules. So I'm going to look at the damper, and I'm also going to select the cooling staged override check. I'm going to look at the connections for both of these. So let's raise this up a little bit. For the damper override check, we know there's only 1 proportional output, and here it is. When you only have 1 like this, the setup is going to be a OR state, or a value of OR. For the cooling staged override check, we have 2 stages. So when the PID algorithm for cooling, if that's going to go into the hold state, it'll have to do it when both of these cooling stages are in override. Because if only 1 is in override, the PID will control the other output point. When both of them are in the override state, that's when the PID goes into the hold state. In order to accomplish that, the setup is an AND function. In other words, both of these inputs have to be in an override state before the outputs are identified as being overridden. So that's the big difference between staged output points and proportional output points, is the OR and the AND function in these state generators. One other thing I'd like to do is to take a look at the objectives one more time and explain each of these objectives. The first objective was, what is the output override monitoring feature? Well, it solves the problem of PRAC trying to tune when the output is overridden. And it does this now by using a PID feedback mechanism to control the output starting value, which is equal to the overridden value. And the components of this feedback mechanism were the miscellaneous input points, which were used to monitor the priority of those output points. That's how it could determine whether it was overridden or not. If it was overridden, then the override check state generators were used to place the PID modules in that hold state via the state table, as well as that value of override went into those control modules. The third objective dealt with what applications use a variation of this feature. What we saw currently in this video is that we saw a cooling percent proportional output, which used the setup OR in its state generator, and we also saw cooling1, cooling2.ec, that was for staged output, and that used the setup AND function. So we saw the setup OR as well as the setup AND state generator module examples. Now, the implementation of this feature, though, it's going to be automatically used when you create a new Release 5 application. It is not automatically going to be added for any of your side loop applications, any custom modules which are manually created, nor is it going to be implemented for any upgraded applications that were created from previous CCT releases. If you do want this feature implemented in any of those three that we just went through, you can read the online help instructions to manually add this feature to your files. And that's the end of this video. Thank you very much.